talk about recycling, especially about the composite here. So recycling in composite manufacturing is one of evolving entrepreneur as a business in this sector, right? Because its sustainability challenge has been addressed by many the country's government. Mandatorily, it should be followed in some cases. And unlike a traditional material, composite have the recycling complexity, very complex, because inside it is not monolithic material. There is two or more constituents combined into one material. So their multi-component nature make us difficult to recycle easily. And, however, the innovative new techniques are being developed to resolve this issue. Okay? So the main methods are like the pyrolysis and the mechanical recycling and the chemical processes. Those are very similar to the conventional materials too. We just slightly reapplied with variation for composite material. Right? So the mechanical method is very direct and very close at our hands. Right? So this is one example of mechanical recycling method. In order to that, this is needles, okay, needle board, and they just punch the product discarded, wasted. Right? Then it can be the fiber web and the many debris will be obtained after all. So after that, this is a CFRP after the needle punched. Okay? So this SEM image of viscose fabric-based needle punched non-woven fabric. So this will be used after some kind of washing process or something like that. Okay? So recycling process chain. So this is waste of composite, then the proprietary patented recycling method is adopted, and is the prepared, and is make into many small pieces, and the next smaller pieces, and the injection mold or other thermoplastic way, this can be used, recycled, and we will have a recycled product. Okay? This is very general process, we can say. The rise of composite material in various industries, lightweight application performance advantages, versatile. Due to those characteristics, we will have more and more composite products, and after that product is finished for the purpose, then it will be discarded. Then it causes environmental concern, and we need have a sustainable solution for that. So landfill is one way usually we do, but this is not so good choice to recycle, because this is not a recycle. This just buried underground. Right? So because the nature of polymer and advanced fibers, its natural decay will be long time taken. That means during we cannot expect the natural degradation within short days, short period. So landfill issue is raised commonly, and resource depletion. So virgin material extraction for composite affect the ecosystem and the resources, right? And the carbon footprint. So production and the disposal of composite both will increase carbon footprint crisis. We need to solve those kind of issues. So current recycling method of composite material is mechanical recycling and the chemical recycling and the pyrolysis. Mechanical recycling like a needle punch method. So grinding, shredding, and the separation a technique mechanically that can separate fiber matrix materials. It's very easily understood. But its result will not be so cleanly washed for recycled. So that means the using as it is would be low quality of, relatively low quality of raw materials can be expected. Usually recycled fiber have less than 80% of its original properties. Less than 80%. That means that is maximum 80 or slightly over 80% of its original strength or stiffness, something like that. So maybe we should expect 60% or at most 70% in general. Right? So, so mechanical recycling itself have some drawbacks, and we can use also chemical recycling. Chemical recycling as a solvent or chemical treatment that should be broken down. Right? So composites break into the return into its original components. So this chemical recycling is I think it looks better than mechanical recycling in the sense of its original property recovered, the level of recovery. Okay? And the pyrolysis means a high temperature decomposition. So in absence of oxygen, then produce valuable product from waste. Okay? That means that this will have tremendously much heat energy is needed. So that means this would be the expensive. And maybe in the process of pyrolysis, we may expect some kind of unwanted pollution. So each of those has its own strength and drawback, of course. Right? So you should choose or combine together to get our product to be satisfied for our purpose. And the limitation and challenge in composite recycling is technical barriers and economic viability and mixed materials. Those three keywords can be considered. And the technology barrier means efficient and cost-effective recycling is needed. Otherwise, the final recycled material would be too expensive. If it is more expensive than its virgin material, the original one, then who will use that recycled one? So that recycled material cost should be reasonable. So in the case of efficiency and cost effective recycling technique is mostly needed. Right? And economic viability means recycling cost often outweigh the value of recovered materials. Right? So that's a little bit linked to the previous viewpoint. So maybe some kind of a benefit may be needed to promote recycling. And that is kind of policy level of support is needed, okay, to overcome this kind of things. And mixed materials, separating different composites to composites is challenging and energy expensive. So we can do, but if it's too expensive, we cannot do. So that's because we enjoyed the strength of fiber reinforced composite, for example. That means between fiber and the matrix have very strong bonding. But recycling means we need to divide it into fiber and the matrix. That means that interface should be resolved, right? So it will be big trouble. That is challenging. That's just a third viewpoint. So innovative recycling technique is continuously coming to us. So advanced sorting technique, bio-based resin, closed loop system, those kind of things are being considered to our society. And the circularity and closed loop economy for composite waste. So design for recycling is needed, and the repurposing and the upcycling should be considered, and the sustainable manufacturing need to be reached. So among those, the design or sustainability is very easily understood, but here's upcycling. Means mostly we say that something should be reused. It means that the performance would be expected to have lower performance than before. Right? That is downcycling. But upcycling means not just recycling. After recycling, through that process, that material should be reborn with higher valued performance. That is upcycling. So that is a function added cycling. Right? So it can be possible together with the very modern design technique and some kind of idea that is needed for. The upcycling is best one. And the strategy for improved design for recyclability. So use of recyclable material means employ resin and fiber with a non-recycling pathway. And the simplified design is minimize complex geometry and using standardized the components. And the material segregation is a design for easy separation of different composites. Okay, to get fiber and matrix separated. And the role of policy and regulation is needed for driving the sustainability. So producer responsibility is emphasized, and the tax incentive is given by policy. Okay, this. And a collaborative effort between industry, academia, and government. Those can be said the research and development is needed as being going on, and knowledge sharing is needed in the same community for the same purpose, and the policy advocacy. It can promote this collaboration better. Okay? And understanding the environmental impact of composite material is important. The carbon footprint is usually emphasized the recent days. And carbon reducing or carbon production means related to money. So carbon footprint it is a method. There is a method to calculate the amount of carbon footprint from that manufacturing or from that kind of activities. So through that you can negotiate with its economic characteristic. And the waste management. The compost can be difficult to recycle because many materials in it, and often end up in landfill as a worst choice. So it's very difficult to get agreements from society these days, and where they can persist for centuries. Okay? That is problem. It is very difficult to be biodegraded naturally, and the resource depletion with another issue. And the advancement in renewable and biodegradable composite constituents, natural fiber, bio-based resin, biodegradable polymer, those are even landfilled. In this case, it can be later biodegraded naturally after some time. Right? So this kind of the raw materials would be beneficial in the sense of the recycling issue or sustainable issue. Okay? And the innovation in manufacturing processes for sustainability is additive manufacturing, because it can reduce the waste of material, and the lightweighting technique, also composite design, can be optimized to reduce material use. And closed loop manufacturing is integrating recycling and reuse as a product life cycle. So all of those related to the use, the minimum amount of materials to produce the product. And enabling circular economy with the composite material recycling, mechanical recycling, chemical recycling, downcycling. Okay? This downcycling is opposite to upcycling. Okay? This downcycling means the composites are repurposed into low value applications, such as filler material, to extend their lifespan and reduce waste. And emerging application of sustainable composite material, alternative aerospace, construction, those kind of things can accept recycled material-based composite again. Okay? So in those areas, this automotive, aerospace, and construction, there are many cases that the recycled material is used for its components already. And the challenge and the limitation in adopting sustainable composites, the cost, okay, main issue, performance, downcycling, upcycling, and scalability, okay, and availability. Those kind are issues, challenge and limitation here. And the government regulation is imposed many times. So CFRP, those kind of things is being required to recycle these days. So there are many related the law from many countries. And the life cycle assessment and the sustainability matrices, environmental impact, carbon footprint, resource efficiency, those kind of terminology can be heard from the article or news. So you may have some understanding about those terminologies. Right? And why composite recycling matter, environmental impact like other waste, and resource conservation. Okay, and this is also common to other waste material, and economic benefit. All of those are very same trend with other the material that need to be recycled. But I think main problem can be resolved with this one. So for example, so this is just a general concept for recycle. So this is kind of plastic, because these days plastic is mostly well recycled material. Right? So plastic waste is transferred to MRF and the recycling center. At the recycling center, it's sorting into many types, and separately there is shredding, washing, melting, reorganization, new product waste. It's a well recycled group is organized and used these days. But this is plastic case. So everybody will understand it, because most of waste from company or the household. So they can understand this. Many times each of those have the very familiar product figure. It will be suggested, so that they can easily classify it when they the trash. But like this is very easy to classify from the ordinary people. It's easier to be recycled. But do you have some understanding about composite materials? If it should be recycled, then how it can be classified like this? So you don't know, you don't have less understanding about this. So from the expert community, maybe there is of many different type of composite systems. So their recycling method may different from mechanical recycling method, or chemical process, or pyrolysis. Which one should be used, or it should be, this is a landfill, something like that. It must be easily classified from household or final use, something like that. That kind of classification advertisement should be in advanced, I guess. So there's a film plastic case. If even the polymer case, if some of those are not well collected from household, then for recycling promotion, some of very easy, understandable advertisement can be found easily. Okay? So we can classify our. But this one, this is the CFRP. It's carbon fiber reinforced polymer. It's one of most the concerned composite materials for recycling. It's very strongly emphasized from government and from experts, because it is mandatorily asked by government. So the CFRP is it's the matrix material. It's mostly use epoxy. Epoxy is a thermosetting. It cannot be hardly the recycled. And or vinyl polyester or polyester. those kind of matrices will be used for CFRP. And carbon is hardly degraded, right? Decayed. And carbon is very strong, and the carbon fiber is very expensive. So even though it after recycled, its fiber get degraded down to 60% of its original property. Still, it is pretty well for using for other purposes. Right? So, and the CFRP is one of mostly commonly used for manufacturing products these days. So, carbon fiber, reinforced polymer, waste is very much emphasized by policy. So there are many efforts to create innovative recycling method for CFRP, because most of manufacturers must follow the regulation. So this CFRP and this EOL is the end of life, and then waste. It can landfill or it's a scrap, it's recycled. Right? And the new material closed loop economy is very needed, right? Rather than just like this kind of the very worst case of the waste the region. Right? So this to make possible this kind of loop, this recycling method, mechanical, thermal, or chemical, so need to very important. Right? So come back to here. Okay. So challenge in recycling composite, especially this that you can find the CFRP related the composite, how to recycle those. Okay? Those kind of issue is easily encountered. So material complexity should be overcome, and a cost and the efficiency and the lack of infrastructure. So all of three are challenging objects to remove for enabling recycling. So a mechanical recycling of composite is grinding, or make it small pieces, and the separation, and the reprocessing, and the extrusion and molding. So most difficult part is this one. It's energy consuming, time consuming. And the chemical recycling method is depolymerization is used, and the purification step, and the recycling step, and the hydrolysis. That is chemical recycling steps. And the thermal recycling of composites, and the incineration, and the pyrolysis, gasification, the incineration. So this is pyrolysis. And the future composite recycling technique, so we need to make it automated. And the new technology is needed to advance technologies in separation, depolymerization, and other technology. And innovation, developing new recycling method will be very welcomed if those are more efficient and cost effective. So, we can imagine how this can be recycled. Then mechanical, the separation is most easily imagined. And the chemical is maybe is a little bit different from non-export people, okay? Because they need chemical process. And the pyrolysis is maybe a little understandable than chemical process. So any kinds of combination or a newly proposed method will be very valuable in this new business sector. And the circular economy and the composite is a design for recycling is needed. That means at the stage of composite design, so it must be considered how it will be full closed loop system. Okay? That kind of effort is required. And the case study in composite recycling, wind turbine blade, this is recycled with the turbine blade. It presents a unique challenge due to their size and material composition. So this size is longer than 50 meters, 60 meters. So how it can be recycled, the size will be one very big challenge. And the automotive composite case, the recycling composite from automotive parts can reduce the use of virgin material and decrease emission. Because automotive industry is its inherent nature is mass production. That means any kinds of component used in automotives means millions over 10 millions of parts produced. That means if recycled material can be used for automotive components, then its reusability will be greatly enhanced. So composite waste collection and sorting, the collection system should be improved like plastic, so that everybody can understand how to classify when they waste those. And the sorting and separation, and the cleaning and the preparation. So those kind of efforts are also needed. So recycled composite application, there's a construction material, automotive parts, consumer products, all kinds of products may be possible from recycled material. So already there are many kinds of recycled material-based product on market, and it has a kind of a marker, marker on the surface of the product, so that it is a little bit better to be sold, because consumers have some caution about it. Right? But composite material case a little bit different than the previous polymer-based monolithics or aluminum or those kind of things. After recycled, it's almost no difference from the previous original one in the sense of material. But composite material, in case of fiber matrix, it cannot be perfectly recovered from its original raw material case. So I think it is not avoidable to have equivalent property of recycled composite material. So we should find more creatively how those can be reused. So maybe by using some upgraded design concept may promote its usability better. Then we can have a kind of upcycling result. And the environmental and the economic benefit is very clear, right? Reduced landfill waste will be the expected, and the economic growth will be obtained because recycling composite, it means it creates a new industry and job, and it can stimulate economic growth and resource recovery. So this recycling, composite recycling business is most new business starting from very few years back, because the mass production of a composite material component, maybe it's around 2010, something like that. Then after 10 years use, the waste will be found much. That means just 4 years back. And the recycled issue of composite material is raised. Then that means this year or last year was the beginning point of recycling business for composite materials. Okay? So that means the method and its the business benefits is not well established. So that is another chance to challenge it. And the conclusion and the future outlook, recycling composite material is very essential for sustainable future, and ongoing research and development are very crucial for improving recycling technology, expanding application, creating a circular economy for composite. So future sustainable composite is bright with continued advances in material science, manufacturing, recycling technology. The focus on sustainable composite material will continue to be an area of intense research and development, driving innovation in a range of industries. So this is about the recycling issue with composite material. So conceptually, okay? It's not all of our lectures. Our purpose is just to provide the conceptual and very the large scale of viewpoint only, not the detailed technique to calculate, analyze, design, or manufacturing the real parts. Those kind of things are not included here. So the purpose of motivation toward the composite material mechanics in various ways. So if you can notice the importance of composite material and its related technology will be crucial to our future. So you have motivation to participate in those communities. Then I think my lecture would have some result. Okay. So do you have any question about recycling or related? Do you have any kinds of? No. Yes. Of course, of course. Because thermoplastic is relatively easy, because the thermoplastic matrix composite means the plastic can be treated at elevated temperature, right? So that means it can be melted and reused. Then the fiber will be the washed and retreated separately. But most of the CFRP related is very hard and very favorable composite. Its matrix is epoxy or vinyl polyester or polyester. So that means it is very difficult to be recycled because it cannot be the thermoplastic like recycled, right? So very different. So maybe epoxy based composite, maybe I don't know. I'm also not have a deep understanding about recycling technique except mechanical needle punch, something like that. It's very easily understandable, but chemical process, maybe it will not be used for CFRP, I guess. Maybe pyrolysis or mechanical method would be used, right? But it is thermoplastic based, then it is much simpler. Okay? It can be answered to you. Okay.
But just because of the temperature and bandwidth, we are not using
I think because thermoplastic, if every composite can be made of thermoplastic, then it would be better for recycling purpose. But the matrix itself has a different characteristic from thermoplastic and thermosetting. So if we have a more rigid and temperature resistant to hot temperature, or the humid absorption, water absorption, those kind of things are considered, then I should choose epoxy-based composite, thermoset-based composite. And also the manufacturing technique is for mass production. So I think epoxy-based composite, so it would be much easier. Other questions? Okay.
We have some standards for testing of the composites. Similarly, when it comes to recycling and reuse of it, is there any policies made across the globe to see that?
I guess at least a CFRP. Carbon-based the reinforcement ones. So it already, some policies reinforced, requested already from European the countries already. And maybe US too.
Most of the times when we go for developing a new materials, we have standards and we use it. But when it comes to recycling, reuse or sustainability, leaving the sustainability part, about the recycling part or reuse of part, it should be like just like how we have uniform standards for characterization of materials. Similarly, for policies also, should be made for recycling and reuse. Otherwise, the entire composite materials, it will be evolving to a next level of it, and the entire world will be made of composites in a sooner time. What are the policies globally, globally that the reuse and recycling, safety of the environment, all that is not discussed at par with the development of these materials?
It's very completing issue, right? For recycling and the productive mass production, it's a very completing issue. But if we follow just one direction, like material itself, product itself, then maybe its price will be very bestly, the costly, just low price is possible. But that means as extra use will be prevailing. It's because it is very cheap. Then a waste will be found much more. Then maybe landfill will be chosen. But landfill one will not decay for a long time. Then at the end, it is very clear for all of us to ask the stop manufacturing for the or make some method to prevent those kind of the anti-sustainability. Right? So if we can expect at the last conclusion, last requirement, then this is 21st century, not 10th century. So we have to be enforced at the beginning stage of technology. So although it is difficult to overcome, but I think it must have some balanced way to find the between easy manufacturing and the keeping environment. It must be balanced. And lastly, about the silicon. So, he absent today. Okay.
Silicon.
I said. Okay, silicon. So he asked about what is suggestion about silicon-based composite, something like that. It can be where it can be used, something like that. But it needs some kind of creative idea. But I don't have any special idea. But I just checked the website about that. Just the pure cylinder. Then there are many silicon. There are many silicon rubbers we are using. But mostly all of those don't to be replaced by the silicon-based composite substrate. But I can see some kind of industrial component like electrical connector or something. It has very complicated shape, and it must be molded together with the electrical wire or something like that. And as far as I know, the liquid silicon injection is difficult for those kind of electrical connector. So maybe that kind of things need to get some silicon like the property, electrical property, and also need some mechanical stiffness. And currently it is difficult to be manufactured. So it is kind of very special trick is needed from the few of company only. So that means it can be considered for silicon-based composite. I wanted to say like that, but I cannot see him. Okay, this will be the end of my lecture series, and I have to say this all over slide. Actually, because I have less understanding about overall lecture or content level about the GIAN, this program. So I asked Dr. Vivek Dimoli to negotiate that content level and the content itself. So he prepared all of slides for me. So I am very much indebted to the Dr. Bin. He prepared most of slide. So I have to say to you. Okay. Thank you very much, Dr. Vivek. So I have to finish this lecture due to your help. Okay. Thank you very much. Okay. Thank you all, and I'll finish my the lecture today. And if you have any suggestion or question, then I'm pleased to communicate with you by your email or any other things. Okay. So feel free to contact me later. Okay. Thank you very much.
For this course, acting as an expert for this course, GIAN course, and specifically for taking out time from his so busy academic engagement for having discussions with the team of international office at NIT Jalandhar. And we had very fruitful discussions with Professor Inha, Professor Chong du from Inha University, as well as Dr. Vivek, and I would like to thank Dr. Vivek also. And I'm very hopeful that all our discussions would culminate into some MOU between the two universities. And also we are hopeful that it will end up into some fruitful structured exchange program at all the three study levels, BTech, MTech as well as postgraduate levels. Once again, I thank him, and I would like to present a small token to Professor Chong du for as a token of gratitude as well as a remembrance to his visit to Punjab and to NIT Jalandhar. So I request Dr. Sunil to please come forward with this small memento. This is actually a painting of Golden Temple of ancient times, Golden Temple of ancient times. So, आइए please. Yes, please. Thank you. Thank you very much, sir. Thanks to Professor Anish also, Dr. Narendra, and all the participants. Thank you so much.
And then we will move to the
For any query or any discussion, you can write to the professor and he will be ready. So he is leaving now, but the session will continue and can take this up.
the last 2-3 days, last 4 to 5 days, you heard that different high performance fibers, para-aramid, Xylon, UHMWP fibers, and these high performance fibers used for the different applications from aerospace to the protective armors and automobile sectors. So this one is the para-aramid fibers, which is the product of DuPont. And you heard that para-aramid means nothing is the Kevlar. Kevlar is the trade name basically. So you heard Kevlar most of the times, but that is nothing. That is the para-aramid, and this is the trade name Kevlar, which is the product of DuPont. And lot of one Russian aramid is also para-aramid is available. Another is the Chinese variant of this material is also available. So you can feel exactly what is how we are saying high performance fibers. How we can compare with, you are aware about the cotton fibers.
Yes.
And you can see. And from the color you can say this is the golden in color, the price is also like that. And the performance price, and this fiber can be used for the armor as well as a fire protective clothing. Suppose that you want to burn this fiber, it will not burn. Okay. So it's not limited to composite only. It can be used for fire protective clothing, fiber reinforced composite, aerospace industry, automotive sectors, right? Then this one is the another aromatic based fibers, that is the PBO, para bisoxazole, and you heard the terminology Xylon, and this is the product of Toyobo, Japan. Initially, the reported performance like modulus and tensile strength of these fibers is I think I can say all fibers whatever available in the world, this has a highest tensile strength and modulus, but the limitation of this fiber is that this is more prone to the hydrolytic degradation. Suppose that when in the if we are keeping the open in the environment, it will absorb the water, and after moisture, and after sometimes it will deteriorate its tensile or mechanical properties basically. So in US Army, after the Kevlar, they have used the Xylon, but due to this problem, this fiber is banned for the protective armors. Nowadays it is used for the fire protective application, but not useful for the bulletproof jacket. Because of hydrolytic degradations. After some time it will deteriorate its performance. After 1 year or 2 years, immediately around 70 to 80% lose in the strength and modulus. So this is not a successful fiber. Even though we have studied in terms of the impact performance, the initial impact performance is better. It's showing better than aramids, but after accelerated aging or then it is the performance and properties is deteriorated. Then these are the different structures. Basically the orthogonal 3D structures. I would look, I think आप लोग mechanical से हो तो you will say कि this is not a 3D structures, but as the textile point of view we are saying this is the 3D structures, because as per the 2-dimensional this is the 3 layers or 4 layers structures basically, and the thickness and one yarn is moving in the Z direction as well. So even though we can also increase the thickness as per the our machine capacity, we can also make the profile structures from the weaving. I think in the last tutorial you have seen those different type of profile structures, and that profile structures, and one structure is the 3D solid structure. So this one comes under the category of 3D solid structures, and maybe sir have explained about that orthogonal or orthogonal structures, interlock structures. That is the 3D solid structures, which can be used for the as a preform for the composite application and for thermoset as well as a thermoplastic composites. Then this one is the 2D woven fabric, and generally in case of the impact performance, woven fabric, 2D woven fabric, and that is the plain woven fabric is most useful because of the in that there are the various designs like plain, twill, satin there in case of the fabric structures, but in case of the plain woven, number of interlacement point is more and it will give a more structural stability. That's why it is most useful for the impact resistance applications. So now I think we can close.
of transparent bar using 3D printing. तो मेरा PhD का वर्क है इस पे. तो ट्रांसपेरेंट पार्ट क्या होते हैं बेसिकली? ट्रांसपेरेंट पार्ट जो लाइट को ट्रांसमिट करते हैं, उनकी एप्लीकेशन क्या है? अब जैसे हम देखेंगे डेली लाइफ से लेके जो इंडस्ट्रियल एप्लीकेशन है, हर जगह ट्रांसपेरेंट पार्ट यूज होते हैं. और सबसे बेसिक एग्जांपल है उनका विंडो. जैसे ये विंडो है, विंडो जैसे यही नहीं होती. विंडो कोई भी पार्ट जो किसी चीज को प्रोटेक्ट कर रहा है और साथ में इंफॉर्मेशन शेयर हो रही है वहां से, तो सारी चीजों को विंडो बोलते हैं. एक जैसे जो कवर होते हैं, लाइट कवर होते हैं, वो उनको भी विंडो ही बोला जाता है, जो क्योंकि वो लाइट को प्रोटेक्ट कर रही है और साथ साथ में लाइट ट्रांसमिट भी हो रही है, तो उसको विंडो बोला जाता है. तो और एप्लीकेशन क्या होगी? जैसे लेंसेज हो गए, ऑटोमोबाइल में हमारे जो लाइट्स हैं उनके कवर हो गए, फिर ये जो लाइट्स हैं उनके डिफ्यूज़र हो गए, वो सारे ट्रांसपेरेंट पार्ट्स में हैं. अब इसमें दो टाइप के पार्ट होते हैं, एक इमेजिंग, एक नॉन इमेजिंग. इमेजिंग पार्ट होते हैं जो इमेज बनाए, जैसे लेंसेज और प्लेन ग्लास जो एग्जैक्ट इमेज बनाता है. लेंसेज आर मैग्नीफाइंग एंड प्लेन ग्लास जो है वो नॉर्मल इमेज बनाएगा. और दूसरा था नॉन इमेजिंग. नॉन इमेजिंग में क्या होता है? जो सिर्फ लाइट ट्रांसमिट कर रहा है, जो इन्फॉर्मेशन ट्रांसमिट कर रहा है, एग्जैक्ट इमेज नहीं बना रहा वो. एग्जाम्पल है डिफ्यूजर. ये लाइट का डिफ्यूजर है. अब ये लाइट है, इसमें डिफ्यूजर लगा है, इसके अंदर नहीं दिख रहा, हमें दिख नहीं रहा, बट लाइट तो ट्रांसमिट हो रही है. पूरी लाइट मोर देन 90% एफिशिएंसी से लाइट ट्रांसमिट हो रही है, तो दे आर नॉन इमेजिंग टाइप. ठीक है. तो अभी जैसे ट्रेडिशनल जो फैब्रिकेशन प्रोसेस है, जैसे हमने बाकी प्रोसेस में पढ़ा है कि कॉम्प्लिकेटेड थोड़े और कम्प्लेक्स पार्ट. जब भी हम कम्प्लेक्स पार्ट की बात करते हैं तो जो कन्वेंशनल प्रोसेस है उनमें कोई ना कोई लिमिटेशन होती है. ठीक है. तो इसलिए मैं एक्सप्लोर कर रहा हूँ 3D प्रिंटिंग फॉर द फैब्रिकेशन ऑफ ट्रांसपेरेंट पार्ट. तो सबसे पहले क्या है? सिलेक्शन ऑफ AM प्रोसेस एंड मटेरियल. तो सबसे बेसिक जो प्रोसेस 3D प्रिंटिंग की FFF वो सिलेक्ट किया है, और ट्रांसपेरेंट PLA लिया है. उसके लिए फ्यूज फिलामेंट फैब्रिकेशन FDM है, उसी का नाम है FFF. FDM जो है वो एक ट्रेडमार्क नेम है. जो स्टेटस से कंपनी है वो जो मशीन बनाएगी उसका नाम FDM होगा. बाकी जो भी मशीन एक्सट्रूजन बेस्ड प्रोसेस होगी सिमिलर प्रिंसिपल फॉलो करेगी, उसका नाम FFF होगा, क्योंकि जो FDM नाम है वो उनका ट्रेडमार्क है. पेटेंट था पहले, बट पेटेंट जैसे 20 साल बाद एक्सपायर हो गया, तो फिर जो बाकी कंपनियां हैं उन्होंने इसको रेप्लिकेट करना स्टार्ट किया, तो उनका नाम वो FDM नहीं दे सकते थे वो, क्योंकि पेटेंट तो 10 या 20 साल बाद एक्सपायर होता है. जो नाम है वो ट्रेडमार्क रहेगा. तो जो जैसे ये मशीन है पीछे, सबसे एंडर 3, इसको FFF बोलेंगे, FDM नहीं बोलेंगे इसको. जो स्टेटस से बनाएगी लेकिन सेम मशीन, उसको FDM बोलेंगे. ठीक है. तो सबसे पहले है, अब जैसे मैं एक एग्जांपल देता हूँ. ये जो पार्ट है ये ट्रांसपेरेंट PLA से बना है, इसको क्लोजली देख लो, बट ये ट्रांसपेरेंट नहीं है. ठीक है. ट्रांसपेरेंट PLA से बने हुए, ट्रांसपेरेंट नहीं. क्यों? क्योंकि अभी तक इसके पैरामीटर नहीं पता हमें कि कौन से पैरामीटर पे जो हमें मैक्सिमम ट्रांसपेरेंसी मिलेगी. तो मैंने सबसे पहले क्या किया, कुछ सिलेक्टिव पैरामीटर सेलेक्ट किए बेस्ड ऑन लिटरेचर, और थोड़े से ट्रायल एक्सपेरिमेंट किए थे. उसके बेसिस पे मैंने 5 पैरामीटर सेलेक्ट किए पहले. उनके ऊपर 1 फैक्टर टाइम लगा कि सभी का इफेक्ट चेक किया कि क्या इफेक्ट आ रहा है. अब ये जो जैसे मान लो हम मैकेनिकल पार्ट को बना रहे हैं, 3D प्रिंटिंग से हम जो भी मैकेनिकल पार्ट बना रहे हैं, जो कोई भी प्रोटोटाइप बना रहे हैं, जैसे कोई भी पंप, तो वो इन्हीं पैरामीटर पे ये पार्ट बना है. अब इसमें ट्रांसपेरेंसी तो है नहीं, तो सबसे पहले क्या किया, वो पैरामीटर फाइंड आउट किए, पैरामीटर की किन पैरामीटर पे हमें मैक्सिमम ट्रांसपेरेंसी मिलेगी. तो रोड विड्थ, लेयर हाइट, एक्सट्रूजन टेम्परेचर, बिल्ड ओरिएंटेशन एंड रास्टर एंगल, ये 5 पैरामीटर सेलेक्ट किए और उनके एक एक का इफेक्ट चेक किया पहले. तो जो 3 मोस्ट इन्फ्लुएंशियल, और इसमें आउटपुट क्या ली मैंने, ट्रांसमिटेंस क्या होती है हमारी, जो कितनी लाइट आ रही है पार्ट पे और कितनी लाइट ट्रांसमिट हो रही है, डायरेक्ट ट्रांसमिटेंस. ये चेक होती है यूवी विजुअल स्पेक्ट्रोफोटोमीटर की हेल्प से. तो इनका इफेक्ट जो आया है, तो इन 5 पैरामीटर में 3 मोस्ट इन्फ्लुएंशियल पैरामीटर आए हमारे पास, लेयर हाइट, रोड विड्थ एंड डिपोजिशन स्पीड. अब इन पैरामीटर को फिर से ऑप्टिमाइज किया विद द हेल्प ऑफ DOE, और उनका इफेक्ट जो है, अब हमारे पास ऑप्टिमाइज पैरामीटर आए. तो ऑप्टिमाइज पैरामीटर के बाद जो हमने पार्ट प्रिंट किए हैं वो ये हैं. अब इन दोनों पार्ट को जब आप कंपेयर करोगे तो जो मिनिमम ट्रांसपेरेंसी थी हमारे पास पहले वो है 12%, बट इसके बाद अचीव हुई हमारे पास 68%।
ये ट्रांसपेरेंसी को आप कैसे नहीं करती?
सर दो मेथड ट्रांसपेरेंसी यूवी विजुअल स्पेक्ट्रोफोटोमीटर की मदद से, जैसे ये पार्ट है हमारे पास, कितनी लाइट इसके ऊपर आ रही है और कितनी इससे ट्रांसमिट हो रही है। एक इंस्ट्रूमेंट आता है यूवी विजुअल स्पेक्ट्रोफोटोमीटर, उसकी हेल्प से मेजर करते हैं, ये डायरेक्ट ट्रांसमिटर्स बोलते हैं इसको। और एक और जो पैरामीटर है दैट इज स्पेशियल रेजोल्यूशन। जैसे मैंने स्टार्टिंग में एग्जांपल दिया आपको इमेजिंग एंड नॉन इमेजिंग ऑप्टिक्स का, तो जो इमेजिंग है उसकी हमें परफॉर्मेंस चेक करते हैं स्पेशियल रेजोल्यूशन से। जैसे ये मैंने डिफ्यूजर का एग्जांपल दिया आपको, अब ये क्या कर रहा है, ये ट्रांसमिट तो कर रहा है लाइट, बट अगर इसकी हेल्प से आप एक डिफ्यूजर लोगे आप, उसके आप देखोगे तो इमेज नहीं दिखेगी सामने, बट लाइट ट्रांसमिट हो रही है मोर देन 90%, बट आपको दिख नहीं रहा कुछ भी, तो वो है नॉन इमेजिंग। तो उसके लिए हम चेक करते हैं स्पेशियल रेजोल्यूशन। स्पेशियल रेजोल्यूशन का एक एग्जांपल दूं मैं आपको, अगर ये एक स्केल आती है, ये स्केल है, सामने देखोगे वो मेरा पोस्टर लगा है, उस पर दिखेगा वो जो फर्स्ट फिगर है, ऐसी फिगर होगी एक सेम। तो इसमें क्या होता है, लाइन पेयर होते हैं हमारे पास। तो स्पेशियल रेजोल्यूशन चेक करते हैं हम कि जो ऑब्जेक्ट जो कंपोनेंट दो लाइन पेयर को मोस्ट सबसे छोटे लाइन पेयर को डिस्ट्रीब्यूट कर दे, तो वो होता है उसका इमेजिंग रेजोल्यूशन। वैसे चेक करते हैं, जैसे मान लो अगर हमें अच्छी इमेजिंग चाहिए किसी, जैसे आप एग्जांपल लो, इसके साथ आप एक प्लेन मिरर लो, तो जो प्लेन मिरर होगा वो छोटे छोटे लाइन पेयर को इक्वली ज्यादा अच्छे से डिस्ट्रीब्यूट करेगा, तो उसका इमेजिंग रेजोल्यूशन ज्यादा होगा। बट अगर सेम टाइम पे आप डिफ्यूजर लोगे, उससे तो दिखेगा नहीं, वो तो ओपेक है, दिखो बेक रहा है, बट एक्चुअली वो ट्रांसपेरेंट है। क्यों? क्योंकि इसका इंटरनल स्ट्रक्चर वैसा है, तो वो इमेज नहीं दिखाएगा, बट वो लाइट ट्रांसमिट करे। तो दो पैरामीटर इसलिए मैंने लिए थे, वन इज ट्रांसमिटेंस एंड सेकंड वन इज स्पेशियल रेजोल्यूशन और इमेजिंग रेजोल्यूशन। तो इमेजिंग रेजोल्यूशन बताता है कि कितनी अच्छी इमेज बना रहा है, एंड ट्रांसमिटेंस इज कितनी लाइट ट्रांसमिट कर रहा है, वो डायरेक्ट ट्रांसमिटेंस कितनी ज्यादा लाइट ट्रांसमिट कर रहा है। अब इन जो डिफरेंट पैरामीटर है उनका इफेक्ट स्टडी किया है कि किस पैरामीटर का सबसे ज्यादा इफेक्ट आ रहा है। तो सबसे ज्यादा इफेक्ट जो है वो लेयर हाइट और रोड विड्थ का आ रहा है। लेयर हाइट का इफेक्ट क्यों ज्यादा आ रहा है? क्योंकि जैसे जैसे हम लेयर हाइट कम कर रहे हैं, तो आपने पहले सीखा होगा कि जो 3D प्रिंटिंग है उसमें पोरोसिटी बनती है, क्योंकि जब लेयर हम लाइन बाय लाइन प्रिंट करते हैं तो दो रास्टर जो होते हैं उनके बीच गैप आता है हमेशा, और जो ऊपर लेयर आएगी, जो रास्टर है उनके बीच गैप होगा, क्योंकि ट्रिपल एफ में हम करते हैं रास्टर बाय रास्टर प्रिंट, तो जो दो रास्टर हैं उनके बीच गैप होगा। तो जब हम लेयर हाइट कम कर रहे हैं तो वो जो गैप है वो कम हो रहा है, तो उसकी वजह से ट्रांसमिटेंस बढ़ रही है। एंड सेकंड इज रोड विड्थ। रोड विड्थ जब हम बढ़ा रहे हैं, जैसे इसी में दिख रहे हैं, लाइन लाइन दिख रही है, लाइन लाइन वो रोड्स हैं, जहाँ रास्टर बोलते हैं उनको। जैसे जैसे हम रास्टर बढ़ा रहे हैं तो जो नंबर ऑफ जैसे में देख रहे हैं आप, जैसे हमने रास्टर बढ़ाया तो नंबर ऑफ वॉइड्स हैं वो कम हो रहे हैं। जो नंबर ऑफ वॉइड्स हैं पहले ज्यादा थे, कम ज्यादा रास्टर होंगे तो ज्यादा वॉइड होंगे, क्योंकि हर दो रास्टर के बाद एक वॉइड है। लेकिन जैसे जैसे हमने रोड विड्थ बढ़ाई तो नंबर ऑफ वॉइड है वो कम हो गए हैं। ये सेम थिकनेस के दो सैंपल हैं, इसमें जो रास्टर की विड्थ है वो कम है, इसमें रास्टर की विड्थ बढ़ गई है। तो जो एयर वॉइड है, क्योंकि बेसिकली क्या होता है, जब लाइट ट्रांसमिट करती है तो एक मटेरियल से दूसरे मटेरियल में जब ट्रांसफर कर रही है तो उसमें जो भी इरेगुलरिटी होगी, जो एयर वॉइड है इरेगुलरिटी है वो, तो वहां पे लॉस होता है। कुछ लॉस क्या होता है, स्कैटरिंग की वजह से या फिर रिफ्लेक्शन की वजह से। तो जैसे जितने ज्यादा इंटरफेस होंगे उतना ज्यादा लाइट का लॉस होगा। क्यों होगा? स्कैटरिंग या फिर रिफ्लेक्शन की वजह से। और मिनिमम जो सबसे कम इफेक्ट आया वो है डिपोजिशन स्पीड का। डिपोजिशन स्पीड का इफेक्ट आता है, बट सबसे मिनिमम क्यों है? क्योंकि जब हम डिपॉजिट कर रहे हैं मटेरियल, तो अगर जल्दी हम मटेरियल तेजी से मटेरियल डिपॉजिट करेंगे तो जो बॉन्डिंग है, दोनों की बॉन्डिंग है, वो एक्चुअली इसमें दिखाया नहीं है मैंने, जो एक पेपर पब्लिश है उसमें बताया है वो। जब मटेरियल डिपॉजिट स्पीड से कर रहे हैं तो क्या होता है, दो रास्टर जो है वो फ्यूज नहीं होते अच्छे से, क्योंकि एक तो मोल्टन स्टेट में है जो करंटली डिपॉजिट हो रहा है और एक सॉलिड में है, तो उन दोनों के बीच में जो बॉन्डिंग है वो अच्छी नहीं होती, उसकी वजह से इफेक्ट आता है, बट वो बड़ा मिनिमम है उन दोनों के कंपैरिजन में। बट अब अगर सिर्फ डिप्रोजेशन स्पीड का इफेक्ट देखेंगे तो वो इन्फ्लुएंशियल है, बट रोड विड्थ और लेयर हाइट के कंपैरिजन में वो मिनिमम है। तो उसके बाद ये हमारे पास आए ऑप्टिमाइज पैरामीटर, लेयर हाइट, मिनिमम लेयर हाइट दैट इज 0.1, मैक्सिमम रोड विड्थ 0.5 एंड मिनिमम डिपोजिशन स्पीड। अब ये जो पैरामीटर है ये मशीन डिपेंडेंट है। अगर हम कोई और मशीन यूज करेंगे या फिर मशीन में कुछ, जैसे हमने नोजल चेंज कर दिया, 0.4 का नोजल है, अगर नोजल चेंज कर दिया 0.6 0.8 के नोजल भी आते हैं, 0.6 mm 0.8 mm के, तो ये वो पैरामीटर उसके अकॉर्डिंग चेंज होंगे। ये एक स्पेसिफिक मशीन के लिए है, ये यूनिवर्सल नहीं है, ये किसी भी ट्रिपल प्रोसेस के लिए ये स्पेसिफिक मशीन बेस्ड है, जो फिक्स पैरामीटर है उनके अकॉर्डिंग है ये। तो अब उसके बाद फिर इसका कंपैरिजन किया है एग्जिस्टिंग लिटरेचर से। तो जैसे मैंने बताया कि ये स्टडी अभी जो 3D प्रिंटिंग है बड़ा कम काम हो रहा है ऑप्टिकल पार्ट मैन्युफैक्चरिंग के ऊपर इसमें, तो कुछ ही स्टडीज हैं और उनके साथ कंपैरिजन किया है मैंने करंट स्टडी का। तो एक रिसर्च है, उन्होंने सिर्फ ट्रांसमिटेंस स्टडी की है और उनकी ट्रांसमिटेंस, मैक्सिमम ट्रांसमिटेंस जो थी वो थी 0.5%, सिर्फ 0.5%। और एक और स्टडी है, उन्होंने ट्रांसमिटेंस और स्पेशल रेजोल्यूशन दोनों स्टडी किया है। ट्रांसमिटेंस उनकी आई थी 52%, बट स्पेशल रेजोल्यूशन उनका आया था 17.8%, जो मेरी स्टडी से ज्यादा था। बट क्यों था ज्यादा? क्योंकि उन्होंने डिफरेंट ओरिएंटेशन में स्टडी किया था। हमने अक्रॉस द रास्टर स्टडी किया है, उन्होंने अलोंग द रास्टर, उन्होंने ऐसे ऑप्टिकल फाइबर यूज किया था इसको। जैसे एक रास्टर है तो उस रास्टर के अलोंग उन्होंने स्टडी किया था, हमने अलोंग द रास्टर स्टडी किया है। हाँ, तो जो रास्टर्स के थ्रू वो लाइट ट्रांसमिट कर रहे थे। एंड एक और था, बट वो डिफरेंट प्रोसेस थी, वो थी लिक्विड बेस्ड आईआर असिस्टेड। आईआर उसमें क्या था, लिक्विड मटेरियल था, तो उस केस में उनका जो स्पेशल रेजोल्यूशन था दैट वाज वेरी हाई, क्योंकि वो लिक्विड बेस्ड प्रोसेस थी। इसका कंपैरिजन फिर आगे किया है अगली स्टडी में। तो अभी ये हमारे पास मैक्सिमम ट्रांसमिटेंस आई है हमारे पास 68.7%। अब ये आगे जो हमारे पास प्रिंटेड एज प्रिंटेड सैंपल है, अब इनकी ट्रांसमिटेंस को इंक्रीज किया है। नेक्स्ट वो कैसे किया है, अब इसका जैसे मैं आपको बताऊंगी। तो जब हमने स्टडी किया तो हमने सरफेस रफनेस भी चेक की साथ में। तो सरफेस रफनेस जो है उसका इफेक्ट भी आ रहा है, क्योंकि जो ट्रांसमिटेंस होती है वो दो प्रॉपर्टी पे डिपेंड करती है, बल्क प्रॉपर्टीज और सरफेस प्रॉपर्टी। अगर सरफेस इरेगुलरिटीज ज्यादा है तो उसका भी इफेक्ट पड़ेगा ट्रांसमिटेंस के ऊपर। तो इसलिए नेक्स्ट हमने क्या किया है, इन पार्ट की पोस्ट प्रोसेसिंग की है, पोस्ट प्रोसेसिंग की है, सरफेस ट्रीटमेंट की है, जिससे और उसका इफेक्ट चेक किया है ट्रांसमिटेंस के ऊपर। तो इसके लिए ट्रायल किए थे हमने सैंडिंग से और केमिकल ट्रीटमेंट से। वैसे और भी मेथड हैं, हमने लेजर फिनिशिंग भी ट्राई किया था। बट लेजर फिनिशिंग क्या हो रहा है, अगर ट्रांसपेरेंट पार्ट है, वैसे जो ओपेक पार्ट होते हैं उससे करते हैं लेजर फिनिशिंग 3D प्रिंटेड की, काफी रिसर्च है इसके ऊपर भी, लेजर फिनिशिंग को 3D प्रिंटेड पार्ट है। बट ट्रांसपेरेंट पार्ट में एक दिक्कत क्या आती है कि लेजर है, लाइट सोर्स है, वो ट्रांसमिट कर रहा है इस सैंपल के थ्रू, तो वो टॉप सरफेस को टारगेट नहीं कर रहा, वो पूरे सैंपल को टारगेट कर रहा है, उससे सैंपल खराब हो रहा है। तो लेजर फिनिशिंग से जो ट्रायल किए थे उससे रिजल्ट अच्छे नहीं आए, तो उसको एलिमिनेट कर दिया फिर हमने। तो हमने सिलेक्ट किया, ट्रायल जब किए तो सैंडिंग से और सॉल्वेंट केमिकल ट्रीटमेंट से, तो उसमें से केमिकल ट्रीटमेंट के रिजल्ट जो आए थे ये कुछ ही सैंपल है, बाकी टेस्टिंग के लिए भेज दिए सैंपल सारे। तो उसमें से फिर हमने 3 सॉल्वेंट लिए जो पीएलए के सॉल्वेंट है, जो पीएलए को डिसॉल्व करते हैं, और उनका इफेक्ट चेक किया विद रिस्पेक्ट टू टाइम। तो हमने सॉल्वेंट लिए हैं इथाइल एसीटेट, क्लोरोफॉर्म और टेट्राहाइड्रोफुरान THF। तो ये कंप्लीट वर्क फ्लो डायग्राम है कि हमने क्या पहले पार्ट प्रिंट किए, प्रिंटेड पार्ट हैं, फिर 3 केमिकल सेलेक्ट किए, हमने मेथड सेलेक्ट किया सॉल्वेंट इमर्शन, डिफरेंट टाइम तक उनको इमर्स किया। उसके बाद उनकी कैरेक्टराइजेशन में हमने ट्रांसमिटेंस, बोथ डायरेक्ट ट्रांसमिटेंस एंड स्पेशल रेजोल्यूशन, डायमेंशनल एक्यूरेसी, सरफेस रफनेस, हार्डनेस, क्योंकि अब जो क्या है केमिकल ट्रीटमेंट होती है वो सरफेस पे इफेक्ट करती है, तो उससे उसकी हार्डनेस पे क्या इफेक्ट पड़ रहा है वो भी चेक किया उसके बाद। एंड सरफेस मॉर्फोलॉजी, तो ये है आफ्टर ट्रीटमेंट के बाद पार्ट में। तो इसमें सरफेस रफनेस पे क्या इफेक्ट आया। अब जैसे दो तीनों सॉल्वेंट है, उनमें से एक है नॉन पोलर, एक है मिड पोलर, एक है पोलर सॉल्वेंट। तो पोलैरिटी बेसिकली उनकी रिएक्शन रेट बता रहा है पीएलए के साथ, जितना ज्यादा पोलर है उतना ज्यादा रिएक्शन रेट है पीएलए के साथ। तो सरफेस रफनेस पे इनिशियली क्या इफेक्ट आया, इनिशियली तो सरफेस रफनेस कम हुई, जो मिड पोलर एंड पोलर सॉल्वेंट है उनके केस में सरफेस रफनेस इनिशियली कम हुई, लेकिन उसके बाद सरफेस रफनेस बढ़ गई। क्यों? क्योंकि जो जिनके साथ रिएक्शन रेट ज्यादा होगा वो इनिशियली तो सरफेस को स्मूथ कर रहे हैं, बट ज्यादा टाइम अगर रिएक्ट करेंगे उसके साथ तो ज्यादा मटेरियल डिसॉल्व हो रहा है, और जो मटेरियल रीफ्लो हो रहा है तो सरफेस खराब हो रही है उसकी वजह से। तो ये दिखाया मटेरियल रीफ्लो का फिनोमेना पूरा। ये है जो ट्रिपलेट के सैंपल होते हैं वो ऐसे होते हैं, रास्टर बाय रास्टर जब बनते हैं, तो ये उनकी मॉर्फोलॉजी होती है सरफेस की। ये सरफेस जो सरफेस हमने चेक की है सेम बता रहा है वो भी। जब मटेरियल रीफ्लो होके फिर मटेरियल सेटल हुआ पीक से वैलीज में, तो सरफेस रफनेस कम हुई। लेकिन जब हम ज्यादा देर तक आप किसी को ट्रीट कर रहे हैं तो क्या हो रहा है, एक्स्ट्रा मटेरियल डिसॉल्व हो रहा है, और वो मटेरियल जब रीसेट होता है तो सरफेस टेंशन जैसी होगी उसी के अकॉर्डिंग मटेरियल रीसेट होगा, वो प्लेन नहीं कभी रीसेट होगा। जैसे हमने मटेरियल को बाहर निकाला, जिस ओरिएंटेशन में था वो वहीं पे वो सेटल हो गया, तो उसकी वजह से सरफेस रफनेस खराब होगी। तो सेम इफेक्ट आया है, उसी की वजह से इफेक्ट आया वो ट्रांसमिटेंस और स्पेशल रेजोल्यूशन भी आया है। कम टाइम पे ट्रांसमिटेंस बढ़ी है, पर उसके बाद ट्रांसमिटेंस कम होगी, क्योंकि सरफेस खराब होगी अगर तो ट्रांसमिटेंस भी कम होगी। और सेम हुआ है स्पेशल रेजोल्यूशन के साथ, इनिशियली स्पेशल रेजोल्यूशन बढ़ा और उसके बाद कम हो गया। और एक ये के इथाइल एस्टेट के केस में ज्यादा इफेक्ट नहीं आया, क्योंकि उसने डिसॉल्व नहीं किया ज्यादा मटेरियल, वो सरफेस मॉर्फोलॉजी में दिखाया है। फर्स्ट वन इज टीएचएफ के केस में जो 20 सेकंड के ऊपर है, बिल्कुल मिनिमम मटेरियल रिफ्लो हुआ है, बिल्कुल मिनिमम मटेरियल रिफ्लो हुआ है। तो जो 40 सेकंड का टाइम है वो ऑप्टिमम टाइम आया है टीएचएफ के केस में। बट क्लोरोफॉर्म के केस में 100 सेकंड पे इतना ज्यादा मटेरियल रिफ्लो हुआ कि उसके जो सरफेस था वो पूरा खराब हो गया। जो माइक्रोस्कोप से स्टडी किया तो जो 100 सेकंड पे हमने क्लोरोफॉर्म पे किया था वो मटेरियल पूरा सरफेस पूरा खराब हो गया ऊपर का, मटेरियल रिफ्लो होकर जब सेटल हुआ है तो वो सरफेस खराब हो गया पूरा ऊपर का। और ईए के केस में क्या हुआ कि प्रेसिपिटेट हो गया, वो जैसे ही ट्रीट किया ईए से तो व्हाइट प्रेसिपिटेट बन गया वो, क्योंकि वो वीक सॉल्वेंट है, और जैसे ही हम उसको सॉल्वेंट को डिप करके बाहर निकाले हैं एयर से रिएक्शन करके वो व्हाइट प्रेसिपिटेट बना रहा है। इसलिए बहुत ट्रांसमिटेंस स्पेशल रेजोल्यूशन बड़ा ज्यादा डिक्रीज हुआ है दोनों के ईए के केस में। और तो सरफेस रफनेस पे इतना इफेक्ट नहीं आया, जब ज्यादा टाइम तक हम इसको ईए से ट्रीट कर रहे हैं तो सरफेस रफनेस बढ़ी नहीं है टाइम के साथ, वो कम ही हुई है हमेशा, क्योंकि इसका रिएक्शन रेट स्लो था। बट सरफेस रफनेस स्मूथ हुई, बट प्रेसिपिटेशन हो गई, वहां पे व्हाइट प्रेसिपिटेट बन गए। जब व्हाइट प्रेसिपिटेट बने तो क्या हुआ, ट्रांसमिटेंस कम होगी, क्योंकि ओपेक वो व्हाइट प्रेसिपिटेट है वो ओपेक है, अंदर से तो मटेरियल ट्रांसपेरेंट ही है, बट जो सरफेस पे व्हाइट प्रेसिपिटेट बने हैं उसकी वजह से वो ट्रांसमिटेंस कम होगी उसकी। तो सेम जो केस स्टडी हमने एक की थी पहले, हमने एक इंटीग्रेटेड लेंस कवर बनाया था इसके लिए। अब इसमें लेंस का इंटीग्रेटेड लेंस कवर क्या है, मल्टी फंक्शनल ऑप्टिकल एलिमेंट है। ये क्या है, ये एक विंडो का काम कर रहा है एट द सेम टाइम, और एट द सेम टाइम ये हाउसिंग का काम भी कर रहा है। ये जो सरफेस है, ये सरफेस है, इसमें जो हमने ऑप्टिमाइज पैरामीटर की उन पे बनाए ये, बट ये आउटर हाउसिंग जो है वो रैंडम पैरामीटर पे बना है कोई भी। तो मेन मल्टी फंक्शन क्या हुआ, दिस सरफेस विल वर्क एज विंडो एंड दिस सरफेस विल वर्क एज हाउसिंग। तो ये मल्टी फंक्शनल ऑप्टिकल कंपोनेंट हुआ एक। अभी मैंने इसमें एक और दिखा सकता था, वैसे मैं इसका जो टूल पाथ था वो दिखा सकता था। उसमें जो ये सरफेस है, इसमें जो हमने पैरामीटर सेलेक्ट किए हैं उन्हीं पे बना है ये, और ये बना है सिर्फ आउटर वॉल से। इसमें इस सरफेस पे कोई पैरामीटर नहीं है, सारे पैरामीटर यहाँ पे हैं। तो ये एक विंडो और साथ में हाउसिंग का काम कर रहा है ये। तो इसमें 11% इंक्रीज है इन ट्रांसमिटेंस। नेक्स्ट क्या है, नैनोफिलर बेस्ड ट्रांसपेरेंट 3D प्रिंटेड पार्ट। तो इसके लिए हमने ZNO लिया है, ZNO नैनोफिलर सिलेक्ट किया है। क्यों? क्योंकि वो होता है यूवी ब्लॉकिंग। जैसे मान लो कोई आपका कंपोनेंट है वो आउटसाइड यूज हो रहा है, सनलाइट में यूज हो रहा है, या फिर आपको स्पेशल यूवी ब्लॉकिंग ट्रांसपेरेंट कंपोनेंट ही बनाने हैं, तो उसके लिए ZNO यूज होता है। तो ZNO यूवी, तो उसके साथ फिर हमने क्या किया है, इसकी 4 कंपोजिशन ली बेस्ड ऑन द लिटरेचर, 1.5%, 2%, 2.5% एंड 3%। तो इसका PU के साथ पहले सोल्यूशन बनाया और फिर जो हमारे ट्रांसपेरेंट पार्ट है उनको ट्रीट किया उसके साथ। अभी इसका जो सैंपल है, इसके बाद के जो सैंपल है वो टेस्टिंग के लिए भेजे हैं इसके बाद आगे के। और एक हमने लिक्विड बेस वाले भी बनाए थे, ये लिक्विड बेस सैंपल है, और इनका जो स्पेशल रेजोल्यूशन है दैट इज अराउंड 700। जो प्रीवियस लिटरेचर में था वो मैक्सिमम अभी तक अचीव हुआ है 360 तक, बट इसका है अराउंड 700 के आसपास।
DLP?
नहीं, एक्सक्लूजन बेस ही है ये भी, DLP नहीं है ये। DLP लेयर बाय लेयर बनाएगा ना। दिस इज अगेन कंपैरिजन करना है तो हम सेम ही प्रोसेस लेंगे। जैसे वो FDM से रास्टर बाय रास्टर बना है, तो ये भी रास्टर बाय रास्टर ही बना है। एक्सक्लूजन बेस ये भी, बस इसमें लिक्विड मटेरियल यूज किया है इंस्टेड ऑफ फिलामेंट।
ज़्यादा बेटर।
हाँ, ये ज़्यादा बेटर है, क्योंकि क्या होता है इस केस में एयर गैप कम है। FDM से जब प्रिंट करते हैं तो एयर गैप आता है, बट इस केस में लिक्विड मटेरियल है, उस केस में मोल्टन प्लास्टिक था, तो लिक्विड मटेरियल उस वॉइड को फिल कर रहा है। जो FDM के केस में वॉइड बन रहे थे, क्योंकि वो तो मोल्टन प्लास्टिक थी, तो वहां पे वो सेटल नहीं हो रहा पूरा, लेकिन यहाँ पे लिक्विड है, लो डेंसिटी DLP रेजिन है ये। तो जो वॉइड बन रहे हैं, एक रास्टर फेयर बना, नेक्स्ट जब लेयर आ रही है तो जो प्रीवियस का जो गैप था वहां पे वो फिल हो रहा है, क्योंकि ये लो विस्कोसिटी रेजिन है, तो वहां पे फ्लो कर रहा है वो, तो जो एयर गैप है उनको फिल कर देगा ये, तो इसका ज्यादा है, इसकी ट्रांसपेरेंसी ज्यादा है।
स्ट्रेंथ भी ज़्यादा है।
हाँ,
स्ट्रेंथ भी ज़्यादा होगा।
नहीं वो अभी
फ्लेक्सिबल
चेक करना है वो अभी।
फ्लेक्सिबल है वो, फ्लेक्सिबल
नहीं, फ्लेक्सिबल नहीं है, थिकनेस कम है इसकी ना, तो लग रहा है फ्लेक्सिबल। ये अगर इसमें भी अगर कम थिकनेस का लोगे वो भी फ्लेक्सिबल है।
अच्छा।
हाँ, उसकी अभी जो स्ट्रेंथ की है, अभी सैंपल भेजिए टेस्टिंग के लिए, उसके बाद रिजल्ट आएंगे उसकी स्ट्रेंथ पे क्या इफेक्ट पड़ रहा है दोनों का, स्ट्रेंथ कंपेरिजन क्या है। DLP से ही नहीं लगा, ये DLP से। तो ये पब्लिकेशन है इस स्टडी से मेरी अभी तक की। अभी 2 और पे काम चल रहा है, 5 हो गई और 2 और पे काम चल रहा है। तो भी मैं बता रहा हूँ कि ये जो नैनो कंप्लीट वाला है एंड जो कंपैरिजन वाला है उस पर अभी काम चल रहा है, बाकी अभी तक का ये काम था। ये भी DLP से बना है, बट ये बिना पैरामीटर ऑप्टिमाइजेशन के बना है ये भी। तो जैसे एक और पार्ट है, अब इसमें क्या है, जैसे नोजल है एक टाइप का, तो अगर इसमें मटेरियल कहीं पे ब्लॉक हो रहा है तो वो भी साथ में दिख जाएगा।
I am a PhD research scholar in the 5th semester. So my work is to print electronic component using additive manufacturing. So electronic component में first of all कोई बताना चाहेगा कि कितने मटेरियल होते हैं किसी भी एक इलेक्ट्रॉनिक कंपोनेंट में?
At least 2. Conducting and non-conducting.
Yes, conducting and not conducting. So to print that 2 materials that is of different property, we need to develop 2 different extruder for depositing 2 different material. So right now in the market, there for liquid 3D printing, there is no any setup available to print 2 different liquid material. other than jet 3D printing is there, na? Do you know jet 3D printing? No, not binder jet. That 3D printer we have in our college also. That uses two different material like UV material, but you cannot change that UV material with the conductive material. So there is a limitation of that machine, that you cannot change the material based on your requirement, because in the electronic component 3D printing you required one material, that is dielectric material. That dielectric material can be polymer. So polymer can be printed using that jet printing, but other one is conductive material. So that machine cannot process that conductive material. So for that we have to develop a machine that can process polymer material also and conductive material. So few initial experiments we have performed in this slide, as you can see here. And before that, one thing I want to tell you that traditionally you can print any electronic component of any shape, of any size, required size, but the process take around 21 days from initial step to final step. So suppose urgently if you need any new design and you need any new part within 2 to 3 days, so it is not possible using traditional manufacturing process, because it takes 21 days to print the final shape. So sometime what happens कि as the technology getting developed day by day, आपके components के arrangement change होते हैं. जैसे जैसे components के arrangement, जैसे आप this is a typical any electronic component. कोई बताना चाहेगा ये किस इलेक्ट्रॉनिक कंपोनेंट पार्ट है? ये देखा होगा आप लोगों ने लैपटॉप का. सपोज लैपटॉप का कंपोनेंट की शेप या साइज अगर आपको चेंज करना है बेस्ड ऑन रिक्वायरमेंट, तो वो न्यू शेप अटेन करने के लिए आपको फिर से 21 डेज का न्यू प्रोसेस आपको फॉलो करना पड़ेगा. बट टू रिड्यूस दैट टाइम हम लोग एडिटिव मैन्युफैक्चरिंग की ओर प्रोसीड किए कि विद द एडिटिव मैन्युफैक्चरिंग वी कैन रिड्यूस दैट मच टाइम. सो अभी के टाइम पे एडिटिव मैन्युफैक्चरिंग का यूज करके इलेक्ट्रॉनिक कंपोनेंट प्रिंट करना, दैट इज अ न्यू डेवलपमेंट काइंड ऑफ थिंग, न्यू इनोवेशन काइंड ऑफ थिंग. बट द लिमिटेशन वाज देयर इज नो एनी 3D printer in India. Outside there is a 3D printer. One company is Dragonfly. They can print any electronic component using additive manufacturing, but the cost is 5 to 6 crore from there. If you import here, it will be more than 7 to 8 crore. So what ISRO plan to fund colleges to manufacture this kind of machine using additive manufacturing. So ISRO have funded us to create a additive manufacturing machine that can print any electronic component. So initial development of the setup, what we did, and one thing is also I want to know that in the electronic component 3D printing there is a two material. One is dielectric material, other one is conductive material. In the dielectric material, if you deposit any liquid polymer, so how much time is required to cure any liquid polymer? Do you know? Normal any epoxy material, how much time it takes to cure, means to solidify? 24 hours. So using additive manufacturing, it is not possible to rapidly 3D print any liquid material. So we switched from normal normal process to UV curing process, because UV based liquid polymer that can cure within seconds, like less than a second it can cure, and it will rapidly increase the time of any manufacturing process. So to the first material, that is dielectric material, we used UV curable material, and second one is conductive material. In the market right now, lot of research was there to print any conductive material. They generally used to go graphene and CNT, carbon nanotube, MWCNT also, but their conductivity is like 10,000 times than normal copper that is manufactured using traditional manufacturing. Normal copper, solid copper, you can see. Do you know the conductivity of solid copper? What is the conductivity of solid copper? It is around like 5 to 6 into 10 to the power 7 Siemens per meter, and no material right now in the market which is near to that. So one company in the IIT Kanpur, Lichotronics, they develop a liquid based material that has a conductivity of near to 2 to 3 into 10 to the power 6 Siemens per meter. So we procured that conductive material from there, and we have printed that conductive material. It is 10 times less conductivity than actual copper, but it is maximum right now in the market, maximum conductivity, so that you can achieve high performance electronic component. Another one material, that is dielectric material, polymer material. We printed normal commercially available UV material, but the dielectric constant of that material was very high. It is near to 10 to 15, but the required dielectric constant was less than 5. So yesterday I was showing that we have mixed glass microsphere in the resin just to increase the viscosity and reduce the dielectric constant. I also shown you the mixing process also yesterday, vortex mixing and sonicator also. So I have mixed that material, and I have performed the rheology testing of that material. See, these are the rheology testing. Viscosity get increased from around 500 to 1600. Viscosity get increased, but the dielectric constant was decreased from 15 to like near to 10, but not achieve the required dielectric constant of less than 5. So these are the few challenges of developing electronic component using additive manufacturing. So these are the material perspective. Now the machine based machine perspective, how we have developed the machine. Initially we put UV material in the syringe, and we have deposit manually with the hand. After deposition we put torch. Torch was there. We put a torch, UV light torch, and the material get cured. We see that that deposition is possible, so we put that torch and syringe over the 3D printer. So this is the process we develop initially. That syringe is there, and next process torch is also there. Here syringe is there, and after deposition we put torch over it, UV torch. So that material gets solidified, but the process parameter was not good initially. So we after certain development we put UV light, 2 UV light over the single nozzle, so that curing can take place. But if you put 2 UV light in an axis, so curing will take place only in that direction. Means 2 UV light in a single line, if you put it, So you can print that material in that line only, not in the at the perpendicular direction. So we developed another process to put all the UV light around the nozzle uniformly. In the angular disc is there, if you know a shape of the angular disc. We distributed light in that form so that you can print UV material in any direction. We have also writing means that design means we have put it for the that patent also for that design. And after developing that UV deposition setup, we have also developed for depositing conductive material. That setup is the right now final prototype setup. So that setup can deposit polymer material, that is UV curable material, and conductive material also.
What is the maximum layer thickness you have?
Maximum or minimum? Minimum. Maximum it can be.
That will be a challenge, I believe.
No, minimum is the challenge. Maximum you can if you increase the nozzle diameter.
The curing of the layer at the top and at the bottom.
Yes, that the penetration effect, shielding effect. That is called. The term is shielding effect. Shielding effect will be there if you increase the layer thickness.
What is the maximum you have?
So maximum layer thickness we have around 0.8 mm, maximum 0.8 mm, and it was also transparent, not opaque
So the
material.
shading effect will ultimately reduce the interfacial bond.
Yes, it is there. So generally our work is to miniaturize any component. So we focus on minimizing the layer height. Yeah, minimizing the layer height. So for polymer we have a minimum layer thickness of 0.1 mm, and for conductive material we have achieved a layer height of 35 micron of using conductive material. And purpose also for using any liquid material also, let me tell you why we have used liquid material, because in liquid material the shear deformation is high as compared to any solid material. So you can miniaturize any part, like you can achieve smaller layer thickness with comparison to any solid material deposition.
Problem is smaller layer thickness is only the process takes a lot of time.
No, but the miniaturized small part you can manufacture. In the electronic component, they are going for a smaller size only. They are reducing the final size.
I'm thinking from the additive manufacturing point of view. The biggest challenge right now I am facing is to match the speed with the conventional manufacturing. So that is, if you look at from that angle, it's always that we have to go for higher layer thickness rather than reducing the layer thickness. So that's why I asked that question. There's nothing special about that.
Yeah, that one challenge is that if you want to print any miniaturized part, so that challenge becomes reversed. Like you have to put the smaller.
There is your requirement is
based on requirement.
Defining that you have to get that into medium number.
So I think yes. In the initial lecture, sir has shown this part also. This part we have printed, and as this setup is means self-developed, like customized setup, so we need to develop the toolpath also, because any commercial 3D printer, you can put CAD model and RSTL file in the Cura software that will ultimately give you code in the form of G codes. So commercial 3D printer, using commercial 3D printer, you don't need toolpath. They already developed by Cura software. But if you develop your own setup, you need toolpath. So toolpath we also developed using MATLAB software, where you can take the coordinates and you can arrange the input condition and output, means initial condition and final condition, and G code in the form of G01, X, Y, Z, extrusion E value, like that. So initially we have printed conductive material to test our toolpath. This is any means circuit board we have printed of only single conductive layer. So this was the parts, and this is also parts. You can see this part, but please don't touch it, otherwise it may get damaged. These are the conductive parts that we have printed initially just to check our toolpath, because customized setup need your own toolpath. So after successfully depositing the conductive material, we have printed this conductive material over the polymer, so that dual material deposition can be possible. This is the copper material.
That one you have done?
It gets oxidized. We perform EDS of that material. So 3% oxidation was happened. It will affect the performance.
Covering of the oxide here.
So
each particle will join with each other, that will add the resistance.
That will happen.
Your path will may get heated.
So
what kind of solution you have for that?
coating can be done after depositing the copper material. The exposed copper.
When you have a copper particle, exposed to the air, it starts oxidizing immediately.
So with this material, only 3% oxidation was happening, because in the ADS the oxygen percentage was showing 3%, and so from that we check the conductivity after printing, and few days we kept our sample few days. After that we checked the conductivity. So conductivity was not reduced that much due to material property. It is not getting oxidized, so advantage is there, because normal copper, if you deposit it will get oxidized. So after successfully printing the single conductive layer, we have printed our sample on a polymer. So bottom layer conductive, in between that is polymer material, UV curable polymer material, and over it is conductive material. So our target is to print 2 to 16 layer of dielectric and conductive material. That is the target given by ISRO to us, to print 2 to 16 layer, minimum 2 layer and maximum 16 layer. And size they also given, they given the catalog also. So material wise we have fulfilled the criteria, but setup wise also get fulfilled, but few things required, like there is a sticky problem is there, coating, what will happen to coating, and we also perform the soldering also, so that after printing any component, we have to put the component, after printing the part, we have to assemble the component over that electronic component. So soldering of this material so that we can assemble the component also. So these are the parts we have printed, and so this overall project require 4 objectives are there. There is a poster also on this work. 4 objectives was there. Just to first one was to develop a UV based 3D printer. Second one is to identify a suitable material for PCB, that is conductive and dielectric ink. And third one is to validate and integrate, that is CAD file loading method, like development, because Commercial 3D printer, you can generate toolpath using Cura software, Archie2Box, but this customized setup, you need your own toolpath because this is your setup. So we have developed toolpath also using MATLAB software, and we have integrated few components. You can see we have connected our circuit with the LED, and we have checked the resistance of that conductive material with while bending. If we bend the material, how the resistance of the conductive material get changed, and we also did the conductivity with the respect to temperature, because if you increase the temperature, you see that you know that the free ions present in the conductive material, they start moving here and there if temperature get increased. So resistance was also getting increased in that case. So if resistance get increased, the conductivity will get reduced. So that graph is also there. We have checked the temperature variation from room temperature to 140 degrees Celsius, and the conductivity get reduced from 1.21 into 10 to the power 6 to 5.13 into 10 to the power 5 Siemens per meter. So based on that, we also published paper. Publication is also there based on that, and we have filed a patent on this setup. That is because this setup is the novel setup that is we have developed. No any setup. So it means
how much cost of this?
That overall development, the cost of the component only around less than 75,000, including all the things, materials, component, assembly, everything.
So you have a whole setup here?
Whole setup.
Below 75,000?
Below 75,000. We didn't do the cost calculation, but we actually in the project, when you purchase anything, we purchase spare parts also. So we spend lot of money.
But as you have applied the patent now, so you must have calculated the cost.
Yes,
because this is the you must have given the comparison now of the existing.
We said applied for process patent only.
Okay.
Process patent, not setup patent.
Okay.
We'll apply later because this is a prototype. We have also give the order for final fabrication of this setup. Yeah, around fabrication cost means the development team once 4 lakh quotation was given to them to develop this setup. So this is the thing. In market, when it will come, it will be more than 10 to 15 lakh. Commercialized. So this is all from my side. If any question.
So, आप कर रहे हैं इस पे काम?
जी सर, मैं काम कर रहा हूँ. So any question is there, you can ask. One that is the ISRO project. This one is the SERV project that Sir was told Dr. Narendra Kumar in his lecture, that we are also printing resin with the continuous fiber. And Sir, in his case study, yes, Sir was there. He was showing the para-aramide. So we are printing that is Kevlar material using resin materials. Means resin is the matrix and that is Kevlar is the filler material. So we are printing this one also. This is the part. We didn't optimize the parameter, but we are trying to achieve a part with the fully optimized parameter. So these are the parts we have printed. Yesterday we have printed this part, and we try to burn it to see that can sustain high temperature. So it was sustaining high temperature, and we try to cut it. It will take lot of effort to cut it also.
What is the matrix material in this
It
case?
is the para-aramide, aramide, the Kevlar material.
Along with Kevlar.
Yeah, so matrix material, that is epoxy material.
That's what I
Epoxy material, normal epoxy material. We have purchased that Kevlar material also. Yes, sir.
Netflix तो बंद होना चाहिए.
Good afternoon, everyone. On behalf of the Industrial and Production Engineering Department of Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, it is my privilege to deliver this valedictory address as we mark the conclusion of this insightful GIAN course on modern composite materials, manufacturing and applications, new generation. As we reflect on the past 6 days, it is truly inspiring to see how this course has brought together professionals, scholars, and students from diverse backgrounds to explore the cutting-edge world of advanced composite materials. From delving into innovating manufacturing techniques like automated fiber placement, AFP, resin infusion, and additive manufacturing, to understanding their application in creating complex geometries and optimizing engineering design. This course has opened our eyes to the endless possibilities that composite technology offers. These sessions were more than lectures, they were gateways to envisioning solutions to the challenges of tomorrow. At the heart of this enriching experience are the individuals who made it all possible. Our esteemed guest of honor and speaker, Professor Chong du Cho. His profound insights and decades of expertise have been invaluable. We are deeply grateful for his time and efforts in making this event so impactful. Our esteemed director, Professor Binod Kumar Konajia, sir, although unable to join us today, his vision and constant support have been instrumental in making this program a success. Our registrar, Professor Ajay Bansal, sir, and Dean of Industry and International Affairs, Professor Mamta Khosla, ma'am, their guidance have been a source of encouragement for all our participants. Our head of department, Dr. Rakesh Kumar, sir, your unwavering support and leadership have ensured the smooth execution of this program. A special thanks to our local GIAN coordinator, Dr. N.K. Srivastava, sir, for his efforts in designing and organizing the course. I would like to request our head of the department, Dr. Rakesh Kumar, Dr. Narendra Kumar, sir, to please felicitate our guest of honor for the today, Dr. N.K. Srivastava, local GIAN coordinator. Deva sir also to join in felicitating sir. Thank you, dignitaries. To our distinguished speakers, mentors, and facilitators, thank you for sharing your expertise and inspiring us to think innovatively. The knowledge you imparted will surely guide us in our respective endeavors. And of course, to the participants, your active involvement, curiosity, and collaborative spirit have truly made this program a success. Your enthusiasm for learning and exploring new ideas was evident throughout, and it has added immense value of this course. Thank you for attending the course. To continuously improve our program and ensure they meet your expectation, we would greatly appreciate your feedback. We would love to hear from you, our valued participant, about your experience in this course. Yes, we request the participant to share his views.
Good afternoon, dignitaries on and off the guys. Myself, Dr. Aravind, actually I'm a native of Kerala. Actually, I'm from Trivandrum. From most southern tip, I have traveled to almost northwestern part of India just to attend this GIAN course. So actually my PhD work was different, but last 1 year I am working on this material. So on that perspective, the lectures were very good. The hands-on, we went to textile compressor sessions were very good. We went to additive manufacturing lab. So the sessions were very fruitful and the tutorial sessions were also very fruitful. So in this regard, I thank all of you who have done hard work for this one, especially Narendra Kumar sir, Anish Sachdeva sir, HODs, GIAN coordinator, textile PhD scholars, whoever have done hard work for this one. I thank all of them. Thank you.
Thank you. Thank you so much.
Good afternoon, everyone. First of all, I congratulate the coordinator of this program for successful completion of this GIAN course, that is Modern Composite Materials Manufacturing and Applications, New Generations. Here I have personally learned the hands-on trainings on different kinds of additive manufacturing processes, which are actually used for various types of different applications, including aerospace. And we have also visited the textile department. Dr. Kamble sir has given the hands-on training, and he has explored so many characterization techniques which will definitely help us in research. And the additive manufacturing laboratory have huge potential, and we have explored so many machines, including ultrasonicator machine, DLP, FDM, and DIW. At last, I just thank to NIT Jalandhar for conducting such programs. I especially thanks to Dr. Anish Sachdeva sir and Dr. Narendra Kumar sir for inviting us. And in future, we expect such more programs where we will be doing our contribution for the successful development of joint ventures. Thank you, sir.
Welcome.
Hi everyone, good afternoon. Myself Vishal. I am from IIT Mandi and doing PhD there. So I joined this course, Modern Composite Materials Manufacturing and Application New Generation. I thanks to all the coordinator, organizer, and all other participants who interacted and shared their views about composite materials. The course was perfectly planned from very basic to advanced level, in which we learned about the composite material, their processing, their application, and even even the recyclability of the composite materials was also shared, which is very necessary part of any material development, so that it can be useful, as well as there be no harm of using it on the environment. So thanks to the organizer. Thank you.
Thank you. Participants, let us proceed with presenting the certificates. I kindly request the dignitaries on the dais, including course coordinator Professor Anish Sachdeva, Dr. Narendra Kumar, Dr. Kamble sir, and our local GIAN coordinator Dr. N.K. Shrivastava sir, to hand out the certificates. First, I would like to request Dr. Gaurav Kumar Dhuria to collect his certificate. Next, Engineer Anand Kumar Mandal. Dr. Saurabh Kumar Yadav. Okay, Mr. Ishant Kalra. Dr. Vikas Ratan. Dr. Bhingole Pramod. Dr. Kiran Kumar. Engineer Mayank Malik. Dr. Arvind Essel. Mr. Vishal Gupta, Mr. Ashish Kumar, Mr. Shubham Kumar, Mr. Vinod Kumar, Mr. Vivek Kumar, Mr. Jashanpreet Singh, Engineer Siddhartha, Mr. Sudhanshu Singh, Ms. Ayushi Gupta, Mr. Abhishek Sharma, Mr. Ram Naresh Shah, Mr. Abhishek Singh, Mr. Dilkush Barwa, Mr. Ghanshyam Das, Mr. Atish Kumar, Mr. Suraj, thank you, participants. Abhishek Sharma, okay. Thank you, sir. Thank you, dignitaries. Yes. As we part ways, let us remember that this is not an ending, but a beginning, a launchpad for applying the knowledge we have gained and continuing to innovate in the field of composite materials. Thank you.